Hey everybody, Jenni and John here. So last class, I was racking my brain to think of a good way to explain energy and to talk about energy. So I enlisted the help of John. And between the two of us, we're going to do our best to confuse you even more. Hopefully not. So we had a rocket problem. And, go ahead.
We had a rocket initially sitting here, and it went up by 500 meters and ended up going with some final speed. It gives you the thrust, the mass, and it asks you to figure out what the final speed is going to be using energy.
So, you know, we have been using energy, and we've been using this energy. Hopefully it looks familiar to you. This really is a special case of, take it, John.
The work energy theorem. It says the change in kinetic energy is always equal to the work done.
And this is always true.
Yes.
There's no special cases.
No.
This is a special case.
It is.
This is not a special case.
No.
So really we should always use this.
You're always using that whether or not you know it.
Okay, let's do it.
Okay. So we're going to look at it from this perspective. So we have to write down the change in kinetic energy.
Everybody remembers kinetic energy?
1/2
mv squared.
Never forget it. It's always useful. Minus the initial kinetic energy. Do I have to do it?
Yeah, of course you have to.
It's just what though?
But come on, write it. Even though we know it started from rest. Now we didn't really say that, but that was an assumption in the problem. So we all know what at rest means, don't we?
Mm-hmm.
I like to do this.
Oh, is it really?
Yeah.
Zero. Yeah.
Zero. Okay.
So that has to be equal to the work.
Now we talk about, remember when we talked about work, it was force times displacement. And it's a special times, when I say times, it's the dot product. So if I went like this, don't cry. he felt some energy. And in this case, I had to work really hard to displace the force of my big strong muscles.
Displaced me.
That's the quick and dirty on work, in case you forgot. So let's talk about work.
So we got work done by you have to take care of all the forces involved. And when you look at this problem, it's got mass, the thing goes up. It talks about the thrust, so you got the work done by the force of thrust. But having mass goes up.
You said force. You said something about force. And you know what I always want to do when you say force? Free body diagram.
Oh, you like those, yeah.
Let's do a free body diagram. If this is the rocket, what force does it feel? Be the rocket. This is what I like to do. It's very simple. Be the rocket. So let's be the rocket. What do you feel? The thrust?
Yeah, the thrust.
What direction?
Up to make the rocket go up.
Let's call it force, thrust. That's kind of a fat rocket.
Yeah.
It's probably feeling something.
That's a really fat rocket.
What do you think it's feeling?
It's weight.
It's weight.
Down.
Always. Always down. So that's the force due to gravity or the weight. I'm just going to call it F sub G. So really, those are our forces that are going to be associated with the work.
So you have to go through and figure out what the work done by each force is.
Now, is it positive or is it negative? I can't keep that straight.
Depends on the displacement, right? And the force. That's the dot product.
That is. So when I slugged you, and I hope your shoulder's okay,
Right.
but when I slugged you, my force, the big muscles, and the displacement were in the same direction. So that means
The work was positive.
now, if my force and displacement were in the opposite direction, it would be
Negative.
So that's how we keep our signs straight for work.
So when we do the other side of the equation, it's going to be, there's no initial kinetic energy, so we still have the final kinetic energy.
And really, that's what we want to find anyway.
Yes, that's kind of what we could underline that.
Yeah.
Sometimes I circle them.
And you know what? Yeah, let's put red.
You like red?
Yeah, okay.
Okay, so then we have to calculate the work done by the force of thrust. So it's always going to be the force
Times the displacement. In this case, we know it's 500 meters. Now the question is, well, let's just write 500. What the
Oh,
heck?
you want to put that in there?
Yeah, why not? So now the question is, what's the sign? So if we go back to our free body diagram, we know we started here at time 1, and we ended up here at time 2. So we went up, and this is up. So our thrust and our displacement are in the same direction, making
Give you a
it
positive amount of work.
so
I can even put a plus in front of that
yeah,
to remind
excellent.
myself of it.
But wait, there's more.
There's another force.
Because there's another force on here.
So we have to add in the work due to gravity also.
But when he says add, I don't know if we really mean add. Because look at the direction of that force and our displacement that went from here to here. So our displacement was up, but this force is down.
Which means the work should be negative. And I'll put a minus sign here.
Excellent. Now,
The displacement was the same though, so.
yeah,
that
okay.
should be the same.
So now we're just going to fill in numbers and do a little algebra, and we're done. How fast can you do it?
Only unknown here is VF.
We know the mass, we know the thrust, and we know the force
What
due
is
to...
the force due to gravity? I could put something in there for that, couldn't I?
Absolutely. It's mg.
Always.
Oh my gosh. Unless we're not on Earth. And then it would be something different. How fast can you do it? Rearrange that algebra. No, wait, John, you're probably going to do something. You're probably just going to use variables to rearrange it so you don't make any math errors like I always do.
Yeah, me keep variables? Never. I would just keep it in variables and then my class would cry.
All right.
We're all good?
Keep it in variables. Really fast.
All right.
Oh man, John's already doing math already here, right here. So remember, this is this times this.
These are the units. I left them off there.
And if he was going to do just, can I do this for a minute?
Yeah.
Can we just use what we have on here just for, let's call that h, and then this is going to be minus force due to gravity times h, and the whole thing is going to be divided by m, and the whole thing is going to be multiplied by 2 because we're going to bring this 2 to the other side of the equation.
I skipped a few steps.
Yeah. And then I'm going to erase that little squared, and I'm going to make this a square root sign, and now we're done. We simply plug in the variables, and we're done. Woohoo! I am tired. We've done a lot of
Work.
work.